Hello, my name is Udvik, and today we're going to go over our second lesson in combinatorics, how to count. Now you might be thinking, I already know how to count, and then 1, 2, 3. And that's true. But most counting problems are harder than that. They involve first knowing what you want to count, and then you have to figure out how to count it. Because they're not just normally just counting groups of items, they're often something harder, like the example I gave earlier. How many possible Rubik's Cube combinations are there? You can't really count 1, 2, 3 because it's probably going to be really big. And that's the importance of counting techniques. But a problem that often occurs when you do counting techniques, or like just randomly do it, is that you end up memorizing. You're less like, okay, this random formula works. Or like you learn a bunch of random tricks that work for certain problems. But I would recommend don't memorize it. Learn and understand it. So now instead of doing 45 different tricks for 45 different problems, you'll know how to do hundreds of different problems just because you'll understand what is counting and how it works. So please don't memorize, understand what's going on. If you're struggling, try doing more problems or read further in. So all these cool techniques are like have cool fancy names and are kind of complicated. But at heart, they're just arithmetic, and they're just like addition, subtraction, multiplication, division, exponentiation, and arithmetic. So let's start with something simple, counting lists of numbers. I know I said not all problems are like that, but it's a good place to start. So let's start with something simple. Pause and see if you can solve it. And once you're solving, unpause and continue. 3, 2, 1. Okay, so you might look at this and be like, this is obvious. There's 18 numbers. And yeah, that was pretty easy. The counting was basically done for us. And our goal for other counting problems is to reduce it to something like this. Something simple. 18 is our answer, and it's like easy to reach. You just count or you just look, oh, there's 18 numbers. And that was done. So what about counting something like this? Well, you can start by either counting it manually, and you would get something like 1, 2, 3, and you would get 23 at the end. But that's kind of slow and it's kind of tedious. So is there like a faster way we can do it? Well, I'm going to write it down. 7, 8, 9, 10, 11, all the way to 29. Well, our goal, or like something that would be nice, if it started with 1 and went like 1, 2, 3 up to a number, because we know to count that already. So how do we do this? We subtract 6 from each term. And now you get 1, 2, 3, all the way to minus 6, 23. And you get the same answer as before. Try to understand how this works. You turned something that you didn't really easily know how to solve, and you turned it into something you do know, which is a nice technique. When presented with something or complicated or that you don't know, try to like make it simple, simplify it into something you do know. So let's try generalizing this. Like, how would this work for any two random numbers? So we're given two positive numbers, a and b, and we want with like b being greater than a, and we have to find how many numbers between them. Well, starting with a, you have a plus 1, a plus 2, up and until b. So now, as the last problem, we want to start with 1 and we want to end with some random number. How do we subtract? What do we subtract? Well, to go from a to 1, you need to subtract a minus 1. So you'd get 1, this will become 2, this will become 3, all the way to b minus a minus 1. And this can be simplified to b minus a plus 1. And that's our formula. B minus a plus 1. So let's test this on a problem. We have our magic formula. Let's go back here. 29 minus 7 plus 1, which is 22 plus 1, which is 23, which is the same answer as before. So now let's go with something harder. How many multiples of 3 are between 62 and 215? So let's just see what multiples are in there. So what's the smallest multiple in there? Well, after 62 is 63. So 63 is the smallest multiple because 63 is divisible. A way you can solve or find that 63 is the smallest is 62 divided by 3 is equal to 10 and 2/3. Okay, so that means 20 and 2/3. And that means the next multiple is going to be the 21st multiple. So you take 21, multiply it by 3, get 63. So that's the smallest one, 63. So now what's the biggest one? So you could either look at all the numbers, find it 213, or let's try using the same technique. 215 divided by 3 is equal to 71 and 2/3. That means the smallest multiple is going to be the 71st multiple. Multiply that by 3, you get 213. So you go all the way to 213. Okay, so all the way to 213. So it look like 63, 66, all the way to 213. So we want it again to change it to a list like 1, 2, so on and so forth. So now, how do we do that? We might start by thinking subtract 62, because that's what we did for all the problems. We always subtracted something and it managed to go. Subtracting 62, however, leaves you with the following list. 1, 4, 7, up to 151, which doesn't really seem that right, especially because it's not 1, 2, it's 1, 4. The way it adds doesn't really work properly. So what we could do instead is to divide the entire thing by 3. And that gives you 21, 22, and now we go to a list that makes sense. And it will go up to 71. Now we know how to count this. 71 minus 21 plus 1 is equal to 51. Now, when I solved this problem the first time, I looked at this cool trick. 215 minus 62 over 3. This is the number of numbers between 215 and 62. And about 1/3 of them are multiples of 3. So this should work, right? And I would get 153 over 3 or 51, which is the same answer. However, the shortcut doesn't always work very well. And I'll show that an example of when it doesn't work in this problem. So, how many multiples of 10 are between 9 and 101? So, the smallest multiple of 10 between 9 and 101 is 10. And if you check our largest, it's 100. So our list looks like, okay, dividing something by 10, dividing it by 10. You got 10 numbers in this list. Pretty easy. Now B. What's the smallest? 20. What's the largest? 100. Dividing it by 10 again, you get 2, 3, dot, 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 up to 10. And if you count this, 10 minus 2 plus 1 is 9. And now we got 9. So, if you actually use our formula, or like the shortcut we created earlier, what do we get? We get 101 minus 9 over 10, which gives you 92 over 10. And you get 9.2 different multiples. And that's why it doesn't work. When you get 9.2, is it 9? Is it 10? We don't really know. That's like the problem with the shortcut. And if you do the same thing between 103 and 11, you'd get the same difference, 92. So you won't really know whether or not it's 10 or 9. So that's why you don't use that shortcut. Now let's go for something slightly harder. Remember, as always, pause and solve it for yourself. And once you're done, unpause. Okay. How many 4-digit numbers are perfect cubes? So like, how do we do this? Well, one way to do it is brute forcing it, which means try every possibility. See every single cube and see whether or not it's 4 digits long. But that's kind of tedious because you're gonna have to check a lot of cubes and multiplying it out. It's a lot of work. Well, let's see what the smallest 4-digit cube and the largest is, and maybe we find a way to do it, because the way we solve the 3-digit and the multiple problems is find the smallest, find the biggest, count how much is between. So let's try to do something like that, simplify it, or use techniques that we might already know. The smallest one, you can find this pretty quickly, is 10 cubed, or 1,000. The largest one is slightly harder, but if you experiment or use trial and error enough, you'll do something like this. 20 cubed is 8,000. Maybe go up a little bit. Can't be that much. So 22 cubed is 10,648 if you compute it. And so it has to be between these two. So you get 21 cubed, which is 9261. And therefore, 9261 would be our biggest number in the list. So our list would look like 1,000, whatever squares after that, or whatever cubes after that, up to 9261. Now, whenever we had multiples, we divided. So now we have exponents. Let's just take the cube root of everything. So you get or we'll just rewrite it. 10 cubed, the number after that's 11 cubed, all the way to 21 cubed. So now, how do we count this? This is probably just 10, 11, up to 21. 21 minus 10 plus 1 is equal to 12. And 12 is our answer. Now, I'm going to give a set of problems. These ones I'm not going to explain as much. I'm just going to quickly solve for the answer. And meanwhile, this is more like a test to see how much you guys understood. So pause, see if you can solve it. If you want to get a piece of scratch paper, you should have one already. And yeah. 3, 2, 1. Well, let's start with how many numbers are on the list. We just used the formula we created, b minus a plus 1. You get 93 minus 36 plus 1 equals 58. And so our answer is 58. Okay, so now, How many numbers are in the list? 4, 6, 8, all the way to 130. So let's divide everything by 2, because they look like multiples of 2. Yes, they are. 4 divided by 2 is 2. So go like 2, 3, 4, all the way to 65. 65 minus 2 plus 1 is 64. So the next answer is 64. So now, this is something harder. We haven't really done negative numbers. But let's see if our formula just applies. Okay, so we got well, if you notice, this is plus 5. And we realize that, wait, they're not evenly divisible. And we could just go along with it, try using fractions. But that looks like a lot of work. So what if we just make it a multiple of 5? Let's just add 3 to that entire thing. So that'll give you negative 30, negative 25, all the way to 60. So now divide everything by 5, negative 6, negative 5, up to 12. And it seems like we can do our subtraction thing. 12 minus negative 6 plus 1. And subtracting by a negative is just adding. So that would be 12 plus 6 plus 1, which is 19. And that is our answer. Now, again, pause, see if you can solve it yourself. And yeah. Okay. So if you solved it, you should unpause. And now, this is kind of weird. Like, we're starting with big numbers, and now we're going to small. Well, again, let's try doing it in something we do know how to solve. We can just reverse the entire list without changing any of the number of numbers in the list. So it'll be 39, 42, 141, 144, 147. So it's plus 3 from each term to the next one. So let's just divide the entire thing by 3. You get 13, 14, up to 47, 48, 49. We can count this without too much work. We get 49 minus 13 plus 1, or 36 plus 1, which is 37. Now, let's go with something harder. Now we're doing fractions. We got 3 and 2/3, 4 and 1/3, 5, 5 and 2/3, up to 27. Now, this is kind of weird if you don't know how to deal with fractions. So let's just get rid of the fractions. Multiply that entire thing by 3. This gives us 11, 13, 15, all the way up to 79 and 81. Now, the difference is 2, but this isn't divisible by 2. So let's just subtract 1, 10, 12, 14, 78, 80. Divide the entire thing by 2, you get 5, 6, 7, up until 39, 40. 40 minus 5 plus 1, 36. And so our answer is 36. Now let's go for some harder problems. This is getting to a little bit harder than we had earlier. And these things are going to be harder than the problems that we went over earlier. So let's see how well you do against it. Pause the video, as always, and see if you can solve it. Okay, so how many positive multiples of 7 are less than 150? So let's see. What's the smallest number in that list? Well, the smallest number in the list is 7. So we start with 7. Now the next number would be 14, 21, up until, well, what's the greatest number less than 150? That's still a multiple of 7. Using our cool trick from earlier, 150 over 7. This gives us 21 and some sevenths. So about 21. So the 21st multiple of it would be 147. And dividing the entire thing by 7, 1, 2, 3, up until 21, there's 21 multiples. multiples. Now, let's go something harder. How many perfect squares are between 50 and 250? So if you just count our multiples, we can find, count our squares, we can find the smallest one. 1 squared 1, 2 squared 4, 3 squared 9, 4 squared 16, up until 8 squared 64. 64 is our smallest number. And then if you continue counting, we would get 10 squared 100, 11 squared 121, 12 squared 144, 13 squared 169. So it would be 12 squared, which is 144. And like always, if you have squares, our best thing is probably just write them as square. 8 squared up until 12 squared. Now, that's 12 minus 8 plus 1, which is 5. So now our next question is, how many odd perfect squares are in that range? Oh, sorry, I did 150. So that would be 150 if the problem was 150. But we have 250 instead. So the perfect squares between 50 and 250 are 64 up until 15 squared, which is 225. Because 16 squared is 256 and it's greater. This is 8 squared up until 15 squared, which is 15 minus 8 plus 1, which is equal to 8. That gives you a good thing to remember. Read the problem properly. So now, this is slightly harder. How many odd perfect squares are between 5 and 211? Well, if you check, the smallest odd perfect square would be 3 squared, 9. Up until the largest odd perfect square, which is 15. Sorry, 13 squared, 169. Odd, remember, because 14 squared would be under, but 14 squared isn't odd. So now we've got 3 squared to 13 squared. But if you write it like that, we might do 13 minus 3 plus 1. So I'm going to say, remind everybody that's 3 squared. 5 squared, 7 squared, up until 13 squared. So now, subtracting 1, you would get 2, 4, Actually, let's take the square roots first to get rid of it. That would give us 3, 5, 7, up until 13. Dividing the entire, subtracting 1 from everything, 2, 4, 6, up until 12. Divide the entire thing by 2, 1, 2, 3, up until 6. So that means our answer is 6. And now a challenge problem. This might seem hard, but I recommend don't quit, continue trying. How many sets of 4 consecutive positive integers are there such that the product of the 4 integers is less than 100,000? 3, 2, 1. Now, where do we even start? Like, how do we even do this? Well, let's see. Is there a good way to approximate this? Well, we got 4 consecutive positive integers. Let's say it's like a times a plus 1 times a plus 2 times a plus 3, which would be 4 numbers. Let's just approximate that to be a to the power of 4. Okay? And if we find powers of 4 that are really close to 10,000, we get 17 to the power of 4, which is 8, 3, 5, 2, 1, and 18 to the power of 4, which is 104, 976. So let's say if you plug in 17, we'll get 17 times 18 times 19 times 20. Let's say 17 to the 4th is about 17. Let's say 17 to the power of 4 is about 16 times 17 times 18 times 19. Okay? And just to check, that value is indeed below 100,000 with the value of 93024. And just to check, the value above that, 17 times 18 times 19 times 20, is greater at 116,280. Which would mean this is the largest set, starting at 16. And the smallest set would start at 1, so it'd be 1, 2, all the way to 16. So therefore, there are 16 values. Now, that is very complicated. Like, where do we even begin? So the first thing to notice was this kind of approximation. Yes, you could try everyone, but it would be faster to do something like 17 to the power of 4 compared to 16 times 17 times 18 times 19. That was the first important step. And then from there, everything fell into place. Once we noticed that 16 was the largest, and we could just count everything normal. So, as I said at the beginning, the first step is to understand what we're counting, and then figure out how to count it. And that's it. And that is how to count. Now, this mainly uses counting sets, and there are many other things to count, and I will create their own videos on it, but this video is running long, so hope you liked it. Bye. Advik out.